Good morning and welcome from sunny Newcastle. My name is Rafal Wrobel. I represent here Newcastle University, and this is a presentation on thermal management of electrical machines using heat pipes, summarizing some of the research activities within Future Electrical Machine Manufacturing Hub Work Package 1.1, realizing novel design freedoms from innovative manufacturing. Let's start with a short introduction to the challenges associated with development of the next generation of electrical machines. The design landscape includes here a number of themes. We have here design for performance, design for cost, design for manufacture, and design for life. And somewhere at the intersection of the individual design targets, there is a design that satisfies to some degree all of those. The key here is to have a good in-depth understanding of a specific application or electrical machine application to provide a well-tailored solution design for application. When reviewing alternative technology forecast and road mapping documents like this one developed by Advanced Propulsion Center UK, here we have a snapshot of which, it is evident that we are faced with a considerable technological challenge. For example, increase in power density of electrical machines by factor of 4 in the next 15 years. Also, decrease in cost and increase in efficiency. Similar trends can be observed for aerospace industry. Here, however, targets for the next generation of electrical machines for power generation and propulsion are even more challenging, with increase of power density by a factor of 7. There is no single technology solution to provide a step change in performance of the future electrical machines. Clearly, a combination of state-of-the-art multidisciplinary design for application, new materials, and manufacturing techniques might bridge the existing performance gap, all of which are investigated across multiple FEMM Hub work packages. In that context, effective thermal management of electrical machines has been recognized as one of the key enabling factors. At Newcastle University, we've been looking at ways of providing a more effective heat transfer in electrical machines as a part of FEMM Hub activities. One of the technologies we've focused on is heat pipe based thermal management. Heat pipes found commercial use across a wide range of applications and industries, including energy storage and preservation systems, nuclear reactors, air conditioning and cooling systems, chemical reactors, data centers, aircraft and spacecraft applications, also vehicle and consumer electronics applications, among others. The commercial use of heat pipes in electrical machines has been less successful, although there was a considerable interest in early 70s. With initial work suggesting up to 20% performance gains. Both reliability and economic landscape at that time prevented successful deployment of heat pipes in electrical machines. For those of you who might be less familiar with heat pipe technology, a couple of words describing heat pipe construction and principles of operation. Heat pipe is a two-phase system, usually constructed as a metallic vessel containing working fluid. On the slide, we have an example of a sinter-wick copper water heat pipe. The evaporator section of the heat pipe is in contact with a heat source. In the context of electrical machines, that could be an electrical winding. The working fluid in that portion of the heat pipe is evaporated and travels towards a condenser. This is caused by the pressure difference across a hot portion and cold portion of the heat pipe. The condenser section of the heat pipe is in contact with heat sink, allowing for the latent heat to be removed, and then the vapor turns into a liquid, which is then pumped via capillary effect in the wick structure back to evaporator. This phase change cycle leads to very high equivalent thermal conductivity along heat pipe, and this is somewhere from 5,000 watts per meter Kelvin to even 100,000 watts per meter Kelvin for very long heat pipes, as compared with a solid copper, which is approximately 400 watts per meter Kelvin. This two-phase change operation provides a very effective heat transport, for example, from windings or from rotor subassemblies in electrical machines, which are particularly challenging when it comes to heat removal. The next slide presents a couple of early examples of electrical machines with heat pipe thermal management. The first one, the figure shown on the slide, it's Siemens patent showing a hollow shaft with embedded rotary heat pipe and the heat removal feature. The second example has been developed by General Electric's company with heat pipes used both on the stator and the rotor. Interestingly here, the rotor heat pipes act also as electrical conductors, a squirrel cage. Both examples showed considerable improvements of the machine output power. Let's have a quick look at more recent work devoted to heat pipes in thermal management of electrical machines. The first example shows heat pipe assisted heat removal. Here focus on the end winding region of a permanent magnet machine. A hybrid grooved sintered copper water heat pipes were employed, showing here both reduced hotspot winding temperature and improved transient operation of the machine. The second example, which I selected here, shows the use of heat pipes in an axial flux generator. The machine pancake-like format makes effective heat removal particularly challenging. A number of heat pipe arrangements were investigated here, showing that the winding outer periphery is the best for the heat pipe location, and when it comes to performance, 20% reduction in winding hotspot temperature has been recorded. That led to 11% increase in output power of the machine. So far, I've shown you the use of heat pipes fabricated using conventional techniques, which to some degree limit how well we can integrate those two subsystems, electrical machine and heat pipe based thermal management. However, the use of modern manufacturing techniques like additive manufacturing enables new design integration avenues, from the discrete component retro-like approach to multifunctional parts and components, for example, windings with integrated cooling. On the slides, we have a number of examples of heat pipes which were additively manufactured. All of these have been developed by Avid Thermal Division of Boyd Corporation, which Newcastle University has been working with. Here, additive manufacturing allowed to achieve improved heat transfer measures, assure more measured fabrication approach, for example, when it comes to a weak design, and high integration with bespoke like vapor chamber designs. The technology survey, a short summary of which I've shared with you, has been followed by a feasibility study. Here the use of the share of heat pipes was investigated to provide either supplementary or primary heat removal mechanism from the machine body. Traction permanent magnet machine has been used here as a demonstrator. Basic data of the machine is listed in the table, and the heat pipe integration within the stator winding assembly is shown schematically on the figure. A number of thermal and electromagnetic analyses have been carried out to assess both the heat transfer and power loss effects in the analyzed machine demonstrator. The figures shown on the slide are an example from a sensitivity analysis of a thermal contact interfaces between various machine subassemblies, which are critical to the overall thermal behavior of the machine. The theoretical findings suggest that in the analyzed machine, 10 to 30% improvement in output power for low and high speed respectively is achievable. And that led us to the final section of this presentation with some observations and conclusions. Clearly, the use of heat pipes in thermal management of electrical machines needs to be considered from the ground up, with tailored design heat pipe solutions such that specific electrical machine application design requirements are met. The heat pipe compatibility with electrical machine environment needs some careful consideration also, particularly when a high level of machine and thermal management system is to be realized. An experimental work related to the theoretical feasibility study, brief outline of which I provided you with, is ongoing. The figure shown on the slide presents a stator winding assembly with heat pipes incorporated. Further activities will include experimentation, closer engagement with industry, and possibly seeking supplementary finding opportunities to enable exploration of more adventurous thermal management concepts with high level of integration in mind. If you found this presentation interesting and would like to find a bit more, here are a couple of my papers from FEMM Hub research. Please do contact me if you have any questions. I look forward to hearing from you. Have a nice day. Bye.